Okay, so if you're prepping for a senior software engineer interview and kind of feeling like drowning in all those like data storage concepts,
Yeah,
well, you're in the right spot today.
right.
We're going to like dissect one of these like super fundamental things that pops up all the time in these interviews,
Mhm.
the inner workings of key value data stores.
You got it.
Think of this as like your own little strategy session. So you can not only like get a deep grasp of the mechanisms, but also be able to talk about it clearly and with confidence when it really matters.
Absolutely. Yeah.
We're going to zero in on how these things achieve crazy efficient data storage and like lightning fast retrieval under the hood, you know.
Yeah, exactly. We'll explore the strategies key value stores use to manage and optimize all the data
All
segments.
right.
And getting these nuances is important, especially when those interviewers start digging into system design choices and like performance trade-offs.
Right.
You got to show them you understand more than just what's on the surface.
Okay, so let's just jump right in with a core concept.
Yeah.
STables, short for sorted string tables.
Right.
Now, if you're thinking, oh, just another log file,
Mm-hmm.
let's be clear here.
Yeah.
What's different is that inside each segment file of an SSTable, all the data is neatly sorted by key.
And that one little thing, making sure the data in each segment is sorted,
Right.
it really opens up some cool efficiencies.
Okay.
Like it makes merging different segments way smoother.
Uh-huh.
It's like the super optimized merging process where you're looking at multiple sorted lists at once.
Yeah.
So picking the next element in the overall sorted order is a breeze.
Makes sense.
Right.
Yeah. And here's where things get really interesting from like an engineering point of view.
Okay.
During this merging, what if the same key pops up in like multiple segments?
Mm-hmm.
How does the system figure out which value is the current one?
That is a key point when you're talking about keeping data consistent.
Right.
When you've got a key spread across multiple segments, the system is built to grab the value from the most recent segment.
Okay.
That's how it handles updates and overwrites so gracefully. Older versions of that key hanging out in earlier segments, they basically get replaced by the newer ones.
So it's kind of like a timeline of the data.
Yeah.
Where the newest entry for a specific key always wins in the combined view.
That's it.
And after these segments are merged, each key usually shows up just once in the final segment, reflecting that latest state rate.
Exactly. The merge operation makes sure that final segment has a single up-to-date value for each key that was in the segments being combined.
Makes sense.
That's crucial for efficient lookups later on.
Yeah. Okay, that brings us naturally to the whole process of compaction and merging.
Yeah.
Sounds like these two work together to keep the data store running smoothly.
Absolutely.
How do they connect?
So compaction works on a single SSTable segment.
Yep.
Its main job is to find and keep only the newest value for every key within that specific segment.
Right.
So even before you merge segments, each one gets its own internal cleanup.
Okay, so if I'm visualizing this right, compaction is like tidying up your own workspace, right?
Mm.
You toss out old drafts and only keep the final version of each document.
Exactly.
And then merging is like bringing together those final documents from different workspaces
Yeah.
into one big organized archive.
That's a great analogy.
Okay.
When you merge these already compacted segments,
Right.
the process makes double sure that only the absolute latest value for each key survives in the new compacted segment.
Uh-huh.
Even if a key had tons of old entries across the original segments,
Right.
only the most current one makes it through.
To really get this, let's use some example data.
Okay,
Let's say we're tracking views on cat videos.
sure.
Okay, so in one segment, Yawn has 500 views,
Okay.
and in a newer segment, it jumps to 511,
Mm-hmm.
Scratch.
Mm-hmm.
Maybe it only shows up in the first segment with 252 views.
Okay.
If we merge these, what do we end up with?
Okay, so the merged segment would have the latest info. So
Roughly.
Yawn would have 511 views, and Scratch would have 252.
Got it.
Now, what if we threw in Mew with 1,000 views in the first segment and 1087 in the second,
Right.
and then Per starting at 2,000 and jumping to 2114 across those same segments?
Okay.
What do you think?
So in the merged segment, Mew would show 1087 views,
Yeah,
and Per would be at 2114.
exactly.
It's all about keeping that most recent state across all the data we're combining.
Yep.
This seems super important for the database's overall health and performance.
It is.
Why is merging so critical in the long run?
There are a couple big reasons.
Okay.
First, without merging, the number of individual segment files would just explode over time.
Yeah.
the system would become a nightmare to manage.
Right.
Imagine trying to find something by digging through thousands and thousands of separate files.
Oh, yeah, that sounds awful.
And second, it makes read performance way better.
Uh-huh.
When you need to grab a key value pair, the system only has to look at a few big merged segments.
Okay.
Instead of maybe sifting through tons of little ones.
Makes sense.
This means fewer disk seeks, which are usually the bottleneck when you're reading data.
So fewer files to check, fewer disk seeks.
Right.
That equals faster response times.
Exactly.
Makes total sense for anyone who cares about how their application performs.
Yeah.
And just to be sure, the data in these newly merged segments stays sorted by key.
Right. Absolutely. The sorted order stays put throughout the whole merge process.
Okay.
And that's not just a coincidence. It's essential for making future merge operations efficient.
Right.
And it also helps with faster lookups within the segments themselves.
It's like a constant optimization engine, always fine-tuning the data storage for better performance.
Yeah, it's like built-in data lifecycle management.
Okay, so we've got these sorted merged segments on disk, the SSTables. Once they're there, what are some of their key characteristics that are important to grasp?
One of the biggest things about SSTables is that they're immutable.
Immutable.
Meaning, once an SSTable is written to disk, it never gets changed directly.
Wow.
If a key in that SSTable needs an update,
Yeah.
that update creates a whole new SSTable.
That's a pretty interesting design choice.
It is.
So if the files themselves don't change, how do you find a specific piece of data in these potentially massive sorted files? Do you have to scan the whole thing every time?
Not at all. SSTables usually use an in-memory index to speed things up.
Okay.
But storing a complete index of every single key in memory, especially with huge data sets,
Right.
that could eat up way too much RAM.
Yeah, that makes sense.
So a more practical way is to use a sparse index.
A sparse index meaning it doesn't track every single key, just a subset. And
Exactly.
so what's the trade-off there?
A sparse index only stores a sample of the keys from the SSTable along with their byte offsets in the file.
Okay.
Think of it like having mile markers on a long highway
Okay.
instead of a sign for every single house.
Makes sense.
You get a general idea of where to go without all that extra overhead.
Right.
The trade-off is you might have to search a bit more within a smaller part of the file,
Yeah.
but it significantly cuts down the memory the index needs.
So if I'm looking for a specific key, how does this sparse index point me to the right spot in the SSTable?
First, the system checks this in-memory sparse index.
Okay.
It searches for the closest key that's less than or equal to the key you're after.
Right.
Once it finds that key in the index, it grabs the byte offset that goes with it.
Okay.
This offset points to a spot in the SSTable file, usually the start of a data block that's likely to hold your target key.
So the index gets me close, and then I got to do a more focused search on disk within that area.
Exactly. The system does a disk seek to that offset.
Uh-huh.
Disk seeks can be slow, so we want to do as few as possible.
Right.
The index ideally limits it to just one seek per lookup. Once the system hits the spot, it then scans sequentially within that block on disk.
Right.
Since the SSTable is sorted, it knows the key it's searching for will be right after the index key, if it's in that block at all.
That's a smart way to balance things.
Yeah.
You're not overloading memory with a full index, and you're not scanning the whole disk for every read.
Right.
It optimizes for both memory and disk I/O.
You got it.
And to squeeze even more storage efficiency and better I/O,
Yeah.
SSTables are often broken down into these compressible blocks, right?
Right.
Like we talked about before.
Yeah.
The sparse index then points to the beginning of those compressed blocks.
Right.
So when you need to read data, the system finds the right block, decompresses it, and then searches for the specific key within that decompressed data.
Exactly.
So the index leads you to a compressed chunk. You decompress it, and then you zero in on your data.
Right.
Sounds very deliberate and optimized.
It is.
Now, we've talked about how data is read from SSTables, but how are these SSTables created in the first place?
Okay.
Where do those initial write operations go?
That's where the MemTable steps in.
The MemTable.
Okay. When you do a write operation, it doesn't go straight to an SSTable on disk.
Right.
It's first added to this in-memory structure called the MemTable.
Gotcha.
The MemTable is usually set up as a balanced tree, like a red-black tree.
That balanced part is key because it makes sure that insertions and lookups in the MemTable stay efficient even as it grows.
Okay.
You avoid the performance hits you'd get with a simple unsorted structure.
Right.
This tree keeps the data sorted by key as new writes come in.
So the MemTable is like a temporary in-memory holding area where all the new writes are kept sorted and easy to access.
Exactly.
And as more and more writes come in, The MemTable gets bigger when it hits a certain size limit,
Right.
often a few megabytes.
Yeah.
Its entire contents are written to disk as a new SSTable file.
Right.
Since the data in the MemTable is already sorted, this flush-to-disk process is pretty fast
It is.
and creates a new sorted segment.
Exactly.
This fresh S-table becomes the most recent segment in the database's storage.
Yep.
Now, what about new write requests while a MemTable is being written to disk?
Okay.
Do they have to wait? Could that cause latency?
No, the system is built to handle this at the same time.
While one MemTable is being flushed to disk as an SSTable,
Yeah.
the system just creates a new MemTable in memory.
Gotcha.
All the new write operations then go to this new active MemTable.
Okay.
So write throughput isn't held back by the disk I/O of the previous MemTable flush.
Makes sense for keeping write performance consistent.
Yeah.
So when a read request pops up, where does the system look first to find the most up-to-date value for a key?
The read path always starts by checking the active MemTable.
Okay.
If the key is there, you've got the newest in-memory value.
Right.
If it's not in the MemTable, the system then goes to the most recent SSTable on disk and then checks older SSTable segments one by one until it finds the key.
Okay.
It's a layered approach, starting with the fastest in memory and then moving to slower but more permanent storage.
So it checks the in-memory buffer first, then systematically goes through the on-disk history,
Yeah.
starting with the newest segments.
Exactly.
That makes sense for getting the most current data.
Right.
You also mentioned something about preventing data loss before the MemTable is written to disk.
Yeah, for data durability, most robust systems use a write-ahead log or WAL.
Oh, the wall.
Every write operation is first added to this log on disk before it goes to the in-memory MemTable.
Okay.
This log isn't usually sorted, it's just for recovery.
Right.
If the database crashes before the MemTable's contents are safely written to an S-table,
Yeah.
the system can replay the actions recorded in the write-ahead log when it restarts.
Gotcha.
That way it rebuilds the MemTable and doesn't lose any data.
Makes sense.
Once the MemTable is saved to an S-table, those entries in the write-ahead log can be cleared out.
So the write-ahead log is like a safety net,
Right.
making sure that even if something unexpected happens, those recent writes aren't lost.
Exactly.
Okay, so we've been talking about S-tables, MemTables, compaction, and merging. It's clear these aren't separate pieces.
Right.
They're part of a bigger architectural pattern.
Right. You got the underlying architecture that uses SSTables and this constant process of merging and compacting sorted files.
Yeah.
It's widely known as the log-structured merge tree, or LSM tree.
The LSM tree.
Yep.
That's a term that comes up a lot when people talk about modern NoSQL databases.
Absolutely.
Sounds like understanding this is key for anyone aiming for a senior role.
It is. This core design principle is the foundation for a ton of popular key value stores, like LevelDB, RocksDB, Apache Cassandra, and Apache HBase.
Right.
Anyone prepping for senior level technical interviews, really understanding LSM trees, especially how S-tables are handled and optimized, that's super valuable.
Okay.
It shows you get the engineering trade-offs involved in building scalable and performant data storage systems, which is exactly what interviewers are looking for at that level.
So for those of you listening who are gearing up for those big interviews, taking the time to really dig into S-tables and the LSM tree architecture is a smart move.
It is.
We've covered a lot today.
Yeah, we have.
Can we do a quick recap of the key concepts?
Sure. We started with SSTables, those sorted immutable data files on disk.
Right.
That sorted property is crucial because it allows for efficient merging, where the system intelligently keeps only the newest value for each key.
Okay.
Compaction optimizes individual segments, making sure only the latest values are there.
Yeah.
Merging combines multiple compacted segments, reducing the number of files and boosting read performance.
Right.
And to speed up lookups in SSTables, we use a sparse in-memory index that points to specific spots in the data files.
Okay.
Initial writes go to an in-memory sorted structure called the MemTable, which gets flushed to disk as a new S-table when it reaches a certain size.
Gotcha.
All these mechanisms are core to the LSM tree architecture, which is the basis for many high-performance key-value databases today.
This has been so insightful.
Yeah, it has.
For our listeners working towards becoming senior software engineers, really grasping these core concepts gives you a crucial way to understand the design and performance factors in modern key-value databases.
It does.
It's the kind of knowledge that could really set you apart in those technical talks.
Absolutely. And it's not just about the interview.
Right.
These concepts are directly relevant when you're making architectural choices,
Yeah.
troubleshooting performance bottlenecks,
Yeah.
or even contributing to systems that use these types of databases.
Before we wrap up, here's a final thought to chew on.
Okay.
How might different compaction strategies in an LSM tree, like size-tiered compaction versus leveled compaction, affect how the system performs under different workload patterns?
Right.
Like write-heavy versus read-heavy situations.
Interesting question.
It's something worth exploring further on your own.
Definitely.
Thanks for joining us for this deep dive.
I had fun.
Me too.